Okay, now for what we have in item number 1, we have the 15th degree of the cosine of x times the sine of x dx. And with the way that this problem is set up, we can go ahead and use substitution so as to cancel out the first order trig function, namely the sine of x. Okay, and so if we set u equal to the cosine of x, okay, again we're going to have that du will be equal to the negative of the sine of x dx, whereupon we have the reciprocal of the negative of the sine of x du is going to replace dx. So for what we have in terms of the follow through, okay, so cosine of x is represented by u, so 15th degree of the cosine of x, this will be u to the 15th, and then we have sine of x, and dx we have du over the negative of the sine of x. Okay, so we had the sines x to cancel out, and do not forget the negative sign, and so we are looking at the negative of the integral of u to the 15th du, and in the substitution variable we have the negative of u to the 16th all over 16 followed by the constants. And once we back substitute the cosine of x for u, again we have the negative of the 16th degree of the cosine of x all over 16 followed by the constant, and thus this will be the final answer for problem number 1. In the case of what we have for item number 2, okay, we're now looking at the integral of the sine of x cubed dx, and this one we can factor out first order sine of x. And so for what we have in this particular setup, we have the integral of the square of the sine of x times the sine of x dx, and to cancel out the first order we can utilize our main Pythagorean identity from the sum of the squares of sine and cosine being equal to 1, and rewriting that Pythagorean identity in terms of sine square x equal to 1 minus the square of the cosine of x. Again we have times the sine of x dx, and so in the setup, so as to cancel out sine of x in problem 2, just like what we did in number 1, okay, again we can set u equal to the cosine of x. And again we have du is equal to the negative of the sine of x dx, and we have du over the negative of the sine of x is equal to dx. And thus what we have upon replacement, we have the integral of 1 minus u to the 2nd, we have the sine of x, then we have times du over the negative of the sine of x, and so we'll have the sines x to cancel out. Again, do not forget the negative sign, and so at this juncture we have the negative of the integral of 1 minus u squared quantity du, and again we can distribute the negative and just rewrite this as the integral of u to the 2nd minus 1 du. And so for what we have in the substitution variable, we have the antiderivatives will be at u to the 3rd over 3 minus u followed by the constant, and with the back substitution it is going to follow that for the integral of the cube of the sine of x, okay, that's going to be the cube of the cosine of x all over 3 minus the cosine of x followed by the constant, and thus this will be the final answer for problem number 2. Now, in the case of what we have for number 3, a bit of a trick one here, for this is perhaps our first trigonometric integration problem that involves a radical. And for what we have in the case of this next item, okay, so we have the integral of the cube of the sine of 3 theta times the square root of the cosine of 3 theta d theta. And looking at what we have here now, we have, at least in terms of integer powers, okay, we have an odd power that is applied to sine, and as we have done previously, okay, we go back to the main Pythagorean identity, factor out a first order and a second order, in this case the sine of 3 theta, and so as we branch out, we're now looking at the integral of the sine of 3 theta times the square of the sine of 3 theta. Again, we have times the square root of the cosine of 3 theta d theta, and so rewriting the square of the sine of 3 theta along the lines of the Pythagorean identity, okay, we have 1 minus the square of the cosine of 3 theta and so for what we have in the setup, okay, is that we can set u equal to the cosine of 3 theta and taking the differential, we have that du is equal to negative 3 times the sine of 3 theta d theta, whereupon we have for d theta that's going to be du over negative 3 times the sine of 3 theta thus in carrying over what we have, okay, we have the integral of the sine of 3 theta times 1 minus u to the second, and for the square root of the cosine of 3 theta we can just render this to u to the 1/2, and as for d theta we can write this as du over negative 3 times the sine of 3 theta, so we can get the sines 3 theta to go out. Okay, but now we're still going to have negative 3 to divide by, and so in carrying out our leading numerical coefficients, we can write initially negative 1/3 times the integral of 1 minus u to the second times u to the 1/2 du, or if you want to make this into a positive fraction, we can write this as 1/3 times the integral, and then taking the negative of 1 minus u squared, we can say we have 1/3 times the integral of u squared minus 1 times u to the 1/2 du, and multiplying by u to the 1/2, okay, we have 1/3 of the integral of u to the 5/2 minus u to the 1/2 du, and in the substitution variable, as we were looking at taking the antiderivatives for u to the 5 halves. Okay, we have u to the 7 halves. And do not forget the coefficient 2/7. And as for negative u to the 1 half, again we have minus 2/3 of u to the 3 halves. And multiplying by 1/3. Okay, this one we have 2/21 times u to the 7 halves minus 2/9 times u to the 3 halves, followed by the constant. And as we back substitute, now we have again, we had substituted u for the cosine of 3 theta, and so in putting back what we have, okay, the final answer is going to wind up being 2/21 times the cosine of 3 theta to the 7 halves minus 2/9 of the cosine of 3 theta to the 3 halves, followed by the constant.